Okay guys, welcome back to the Population Ecology Lecture Series. We've been really talking about these dynamics as being parameterized by what happens in the host. And now we're going to flip the script a little bit and think about what happens from the perspective of the parasite. And there's really two ways that we can think about the population growth of parasite populations. One is that they have rapid reproduction inside hosts, and two, they have variable transmission into hosts. Now, these SIR models do a really good job of addressing number two, but we also need to think about number one here. And that's where we get into R0. And you have probably heard a lot about R0 in the news related to COVID-19. And just so you know, that R0 it means something different from how we've been using it for our density-independent population growth models. Here, what we're thinking about is the reproductive rate of the parasite. Okay, so R0 is going to equal beta. So remember, that's the rate at which individuals go from susceptible into infected times the population size of the susceptible individuals divided by alpha divided by alpha plus D plus V. Okay, so if we're thinking about this denominator here, alpha, remember, is the death rate from infection of the host. The D is the death rate of the host that's unrelated to infection. And V is the rate that infected individuals are moving into that recovered individual pot. And so this is really the inputs into the infected bin divided by the outputs. That's it. So let's think about for a moment what happens if R0 is less than 1. So hopefully you guys thought about it for a moment and saw that if R0 is less than 1, then that parasite goes locally extinct or extirpates. Okay, so what that means is that with all of these dynamics in mind, we can think about how we figure out what density of the host is needed in order for the microparasite to become sustained, so this R0 doesn't go below 1. So that's what we call microparasite persistence, or you'll sometimes hear people talk about S of T also as the disease threshold. Okay, so what is that equal to? Well, S of T alpha plus D plus V. So this denominator divided by beta, which is right here. So really what we've done is reorganize this equation to get into our threshold population size. So you can start thinking about if S is equal to S of t, then we're going to expect that we're at threshold, so we just have persistence. And if it's more than S of t, then we might have population growth of the parasite. And again, if it goes under S of t, we would expect to get into an R naught less than 1. Okay, so that's what we have from the perspective of the parasite. Now, in our last lecture of this module, I will go over the assumptions of this model, and then we will play around with the model in Populus. So have a nice time. I will see you very soon. Thanks for your attention.